Hello and welcome to the start of our Insight series. Over the next 2 hours, we will present you with more details on selected solutions in 4 sessions. You can see the program and the starting times here on this platform right below the live stream window. And we are starting with a topic that was a real highlight in our last episode of It's Tool Time. It's about high dynamic turning and free turn, the revolution in machining. Dr. Uwe Schleinkofer, Director of Research and Development from the Cutting Tools team, provided an exciting lecture on this, which we were about to present to you now. If you have any questions, do not hesitate to ask us in the live chat. Our expert in the online editorial office will answer you as soon as possible. And feel free to ask the questions in your chosen language. In addition, you can always use one of the contact options below on this platform. Click on one of the options, choose the topic that interests you, and the corresponding specialist will contact you as soon as possible. But now, let's begin our Insight series with Dr. Uwe Schleinkofer and enjoy high dynamic turning with the FreeTurn Tools of CERATIZIT, the revolution in machining.
I'd like to welcome you, everybody, and welcome to the presentation of the high dynamic turning with FreeTurn. I'd like to start right away with a short video which show you the possibilities with the tool. And you see here now the manufacturing of a chess figure. It's a king. And maybe you get already the glimpse of an idea what's behind the tool system. As you see, the flexibility is extremely high, and you can move a turning tool like never seen before, basically. But the turning process is still always the same. And the idea behind that is, how can we change that by using existing technologies on the market with regard to the machines which are available on the market. And the revolution is pretty simple. And when we had the idea the first time, which is pretty long ago, I said, boys, this is crazy, because we put the turning tool in the milling spindle of a multi-purpose machine, basically. So when you look here on the tool, you see the insert, and in the back, the tool is on a monoblock variant directly in the milling spindle. And with that, you have much more options, of course, when you compare that to a conventional turning tool. And with that information, I show you again a small video where we can show you that FreeTurn moves the turning from the XZ level to the YZ level. FreeTurn uses the Y-axis and the milling spindle for turning. And in the video, you see how this is working. The tool, in this case, is HSKT connection. This is clamped in the milling spindle. The center of the insert and the rotation axis of the spindle are in line. This is offering a huge flexibility while turning. And now I show you that. And you see as well, when you are approaching the revolver in the back, the clamping device, the collusion of the tool is avoided by turning the tool, the tip, the not in use tip, away from the clamping. And so you can run until you get to the revolver. It's just a very simple example how you can use FreeTurn. And now I'd like to go a little bit deeper inside this idea, inside this process. So number one, with that, you can save a lot of tools, because you have so much flexibility that you can cover basically every tool with that FreeTurn tool. So you reduce the amount of tools you need during your turning process significantly. So what additional is interesting is you have much less tool places required. So in your revolver, you have, in your tool revolver, you have much more space for additional sister tools, for example, to run here. And with that, I show you that later, you can reduce the empty travel. So the time when the cutting edge is not in the material significantly. And for that, I show you the reduced downtime as well in an example later on in this presentation. Okay, so I mentioned less tools, less empty travel, less time in the manufacturing process, and why that is the way I show you later on as well, leads of course to an increased productivity when you use this tool in technical application. One example is that now with that process, you can use left hand and right hand tools at the same time, because you can turn the tool in the right direction during the process. And you can use the tool additionally in the back or the front of the rotating tool which you'd like to manufacture. So this is a big advantage as well. So another thing is, I mentioned the tool holder in the machine, the tool revolver. Here you have maybe the smallest tool change system in the world, because here we have an insert, and this is available, where we have two cutting edges with a roughing chip geometry and a roughing geometry at all. And we have one tip here with a finishing application incorporated in one insert. So when one roughing edge is worn, you don't have to stop the process. You can right away use the second one for roughing. And when you go from roughing to finishing, you don't have to change the tool. You go from this roughing edge to the finishing edge in one step, and then you are fine. And with that, you can use, of course, much more open options in one tool compared to a single standard ISO turning holder, where when the edge is worn, you at least have to change or turn the insert in the tool holder. So how does this look in an example? This is shown here. It's DMG, Deckelmaho, Mori, CTX Beta 800 TC. This is a pretty normal state-of-the-art machine, nothing special. And we have a steel material. It's 42 chrome molybdenum 4. And I show you here now the application. By the way, we look from underneath to the top of the machine. So the camera is lying on the floor of the machine, which gives, of course, a very nice chip evacuation. You see the chips are falling directly to the camera. So we are preparing now a steel shaft, and we do that in various steps. And you see now, like the FreeTurn tool is moving back and forth to open this pocket. So we're going from the left to the right and machine with that, and we reduce, of course, the time where the cutting edge is not in the material significantly. And you see also that we change the approach angle all the time. So now we are going to the finishing, and we profile the surface. Now we're making a notch. Now we're moving further, going inside the 90 degrees. Now we're cleaning up the surface of this part. Now we're going down the finishing process, and now we are done. We could even do a groove in the notch in the back when we move the insert inside with the right approach angle. So this is another option, we have to run notches as well, which is not possible when you have a right-hand tool. You even can't go there with the tool. You have to change the tool for that. So the second, this is the same part. We are turning now the profile on the left side. The component is the same shaft, basically. The main cutting edge is following the profile with constant approach angle. You will see that in the video. And the result is a very good chip control, and the chip is very similar while turning the profile. And due to the tool is adapting to the profile, we really can make sure that the profile is closed without any interruptions. And it is always the same tool in action from the last video to this video. Now I show it to you. You see, we are following the contour. We are following the contour again. And you see also that the surface which resulting out of that is really nice. Okay, so this gives you a little bit an idea what's behind that, but there is much, much more. And I'd like to step inside these additional informations now. And one of them is you can run with this tool much higher feed rates with perfect chip control. And why is that? The perfect chip control is dependent on the approach angle. This is clear. But the feed which you can use is also dependent on the approach angle, because you can control the chip thickness with that. So you can now choose the chip thickness, the approach angle, the chip formation, and the chip orientation during the forming. I have a nice simulation later on. I can show you that. And all of that gives you now the option to control the turning process much, much better compared to the conventional way. I show you here now 3 different approach angles, and HM written in red on the bottom of the slide shows you the chip thickness. And of course, when you change the approach angle, you change the thickness of the chip, and the length, the cutting edge, is in operation with that. And with that, you can run different feed rates. Right here, you see now for a feed rate of 0.25, we have an average chip thickness by these approach angles. And now we analyzed and checked in our test facility all the different approach angles and analyzed what are the required feed rates to get the best cutting process out of the tool. And this results in, we call that starting curves. So when a customer starts with a tool, he takes this curves here, his graphs, and in these graphs he can see directly under which approach angle which feed rate is the best to choose. And that for steel, stainless steel, and non-ferrous materials with cutting speeds here with the strength and hardness of the material and so on. And you see now that these curves are pretty much bent. That means when you change the approach angle, you reduce the approach angle, your feed rate is going up significantly. That can go up to a value of more than double the feed rate when you go from a conventional tool to 40 degrees here, for example. So you moving or you changing during the application your approach angle, and you can change your feed rate, and with that the efficiency of your cutting process significantly. I give you now afterwards some data which show that pretty impressive how much you can change that. And these data you see here on the slide, they are not theory. they're all tested in live conditions. So now it's not only the approach angle and the feed rate, it is also the chip control. And you see that here now in pictures that the chip formation changes completely during that application. And keep in mind, these are snapshots. You can change that dynamic. So you can move it from one direction to another constantly. So you can change also the chip formation constantly during the process, which gives you another degree of freeness to liberty to control the cutting process. And to show you the chip formation, because pictures are a little bit one side of the story, I show you a simulation of that. That is shown here for an approach angle of 45 degrees and 95 degrees. And you can compare it directly. And you can compare it also with the picture, of course. And you see now when you change that dynamically, you can adjust it directly for the perfect chip formation and for the perfect chip orientation direction in which the chip is flowing during the application. Okay. So now I'd like to show you that also a little bit in a video. So how does the FreeTurn help you to control the chips? And you see now the same what I presented to you in a slide now in a video. You see the thickness of the chip dependent on the approach angle from 80, 60 to 40 degrees. And you see that it is completely different. So now, how does FreeTurn help you to speed up the machine? Of course, you can run with the lower approach angles much more feed rates. And that's now shown here in that video. Everything is the same speed of the video. And you see you save half of the time of the 80-degree approach angle. And this is quite a big gain of time during an application. And another video for that. Now again, you see the thickness and the chip formation, which is completely different. Okay. So now we have another big advantage of this process and this idea, and this is called significant higher stability, which is quite surprising when you look at the tool, because the tool is very long, is very slim, and it doesn't look like it is very stable. And honestly, when we checked it the first time here years ago on an EMCO Hyperturn machine, during the first tests, we were pretty scared, and we are not sure if this is working. But you hear immediately when the tool is in application, it's such a nice turning sound during the application. And I'd like to describe you a little bit why it is that way compared to a conventional turning tool. So as I mentioned, we have a unique design. We have a slim shank. We have the insert on top, and this is pretty long. And we have cooling channels, of course, where we can spread the fluid on the flanks of the insert, where it's most efficient during the application. And you have the tool interface. So why is that much more stable than a conventional tool? And this is pretty easy to describe when you look at the cutting forces, because now we tilt the main cutting force from a perpendicular approach, so 90 degrees, directly in the tool axis. So the pressure is going directly in the tool axis in the spindle. And this gives you much more stability because it's rigid, it's pressed inside the process. And this is much better compared to this cantilever approach, what a normal turning tool is experiencing, because it's always this movement. Now with FreeTurn, we have this movement, and this is much better for a cutting process. And we prepared a small video for that you can get a better impression of the distribution of these forces. You see now the axial, radial, and main cutting force on a FreeTurn tool. And now you see we have the high approach. Now we go to a low approach, and you see on the right side how the forces are changing. They're changing only in axial and radial, and the main cutting force is always the biggest force going directly in the tool. So you can change the axial and radial by using the approach angle, and the main cutting force is always the highest. And now the change of the approach angle again. We start with 90 degrees, and the force on the edge is very high. And now you reduce it. You distribute the cutting process on a longer cutting edge. And now it's a left hand in use. So the force is going down. And now you're using the same as a right hand. So now the wear is on the opposite side of the insert. So we have a reduced force on the edge. We have optimal use of the cutting edge because the wear is distributed on the whole area of the insert. And this is pretty nice. And you can adjust that also with the flexible applications, of course. Now, speaking about the cutting forces, what we did here is we prepared a conventional tool. It's on the top, and we prepared a FreeTurn tool. It's on the bottom, and we prepared it that way that it is possible to mount that on a Kistler platform. This is the blue ring in the slide, and we ran a conventional cutting process, which is shown here. It's the video. Now both videos are running, and here are the conditions. So it's a conventional, not really sophisticated cutting process. Is a pretty normal thing to do. And with these Kistler platforms on both tests, we're now able to compare a conventional turning process with a FreeTurn HDT process. And I'd like to share you now with the results. And this is quite interesting to see. In the red field of the table, you see the resulting cutting forces resulting out of every axis. So this is not really surprising that the cutting forces for both systems are basically the same when you use the same cutting data. So this is clear. But the interesting point is now that the FZ, the blue arrow, this means the main cutting force inside the tool is completely different. When you look at the FreeTurn on the left, the main cutting force is nearly to 2000 Newton. And on the right side for a conventional tool, it's axial and radial force, the FXY, is more than 2000 Newton. So the main cutting force is much lower here, which gives you an idea with regard to the stability that it is much more difficult to get a stable condition on a conventional tool, because your main cutting force is not the driving force of the stability, it's the X and Y force. Another interesting finding what we have is the torque you need to hold the tool in position, because this is also one concern when you see the FreeTurn tool. Is my milling spindle able to hold the insert during the turning process in the position with the torque of the spindle. And this was quite surprising. And it's always the same. The force, the torque you need to hold a FreeTurn tool in position is crazy low. So here, for example, for conventional application, it's just 5 Newton meters. It's basically nothing. Even when you have conventional tools, it's much more, in that case, 25 Newton meter to hold the turning tool in position. So you have a lot of advantages with regard to the cutting forces here. I'd like to thank you for your attention. I hope you got the impression that we are really excited with regard to that idea. And we think we might be able to change a little bit the very old conventional turning process to a much more modern process, which gives you much more option to be effective and to run the processes in manufacturing much. You shift that in a positive way, and we hope and we think that this might be a giant leap in turning in the future.
An exciting lecture and a really impressive innovation for the machining industry. If one of you has already had their own personal experience with FreeTurn, let us know and leave us your comment in the live chat. But in addition to FreeTurn, we have also prepared other insights with which CERATIZIT can help optimize your own processes. Stay tuned, we'll see you here again in a minute.